Hi, everybody. Good morning. I'm happy to see you all. I just want to say, after 2 years, maybe this is the thing that leads me to finally catch COVID, and it'll be worth it. It's worth it. Famous last words, I guess. Okay, so by the way, that first sentence, I memorized it per Catherine McKinley. Good morning, everyone. By the way, that was the opening sentence. All right, so some of you may know this dog. I hope there's some Simpsons fans in the audience. If not, it's going to be a long talk. So this is Santa's little helper. The Simpsons adopted Santa's little helper. He's been a core part of their family now for the past 30 years. It's a successful adoption. Now, I trust that many of you too want to get your research adopted, right? But you can't just publish a paper and count on your work getting adopted, right? Because it's so cute and adorable. You know, people from the outside world aren't necessarily just going to show up, read your paper, and say, "Oh, this is such a great thing." It happens. It happens. But often you have to do more to get your research adopted. So in this talk, I'll be talking about some lessons I learned along the way about how to get research adopted. These are lessons that I think all of you can apply. And of course, following these lessons is not going to guarantee adoption, but I think it helps. So step one, obviously, is shave your head. So all right. I think you may be able to do this without shaving your head. Mike and I have an agreement that this is clearly required. But you do have to get off the couch. All right. And so in the spirit of The Simpsons, this talk is based on the motto, the famous motto inspired by the great Jebediah Springfield, founder of Springfield, who said, "A noble spirit embiggens the smallest man." Now, some of you may be unfamiliar with this word. It is, of course, an actual word in the dictionary. And it means to make bigger or more expansive. And so the goal of this talk is to help you embiggen your research. And it's actually organized around the acronym. So I'm going to go through all the letters of embiggens first and talk about how you can embiggen your research. All right, so step one, embed yourself. So what do I mean by embedding yourself? I mean things like internships, spending a summer month if you're a faculty member, spending a full sabbatical. If you go out into the world and you go into, say, a company or a place like Microsoft Research, where I've spent a lot of time, this is a great way to get your research adopted because you're there. And you may be able to actually help productize your thing by your physical presence, right? And you're connected up with all the people. Doing these things is intensely gratifying on a personal level. I strongly recommend everybody out there to, if you're a grad student, try to do an internship at one of these places. And if you're a faculty member, really consider spending some time in one of these places. It's really worth it. Okay, G, so M, not G, unfortunately. Go to the mountain. So you know the well-known expression, if the mountain won't come to Homer, then Homer has to go to the mountain. So by the mountain here, I mean real users. So this is to say potential adopters of your research. So we're all here at PLDI, and PLDI is great. It's really great, but it's not necessarily where your real users are or the people who are going to adopt your research. By contrast, there's tons of conferences out there, these industry conferences that have all sorts of things about Rust and Python and JavaScript and you name a language or a technology, there's an industry conference for it. And there's languages and platforms and systems. So this is where practitioners go, right? So there's not that many practitioners in this room, but in those rooms, there's like no academics. It's all practitioners. But they're looking for solutions to their problems. They're really interested in what we do. So giving a talk at one of these conferences is a great way to meet potential users and learn from their problems and their concerns. And this can really help inform your research and drive adoption. The first industry talk I gave, this was actually due to Catherine's suggestion, was at Strange Loop. And it was a great experience. So the audience was insanely engaged. They laughed at all the right jokes. It was great. And the crowd was just super, super interested. They posted on YouTube, and also the production team, insane. It looks great. They made me look really good. And it's gotten 300,000 views, which is crazy. But here's the really interesting part. So the top 4 out of the top 6 most popular talks at Strange Loop of all time are by PL people, right? So these are people, like there's all these people at Strange Loop who might want to adopt your work, and they want to see PL people. So it's really easy to apply to give a talk. They pay your way if they accept. Can you imagine? right? Like you go to give a talk at a conference and they pay for your travel. They actually arrange your travel. It's ridiculous. It's a whole different world, that's for sure. Anyway, I highly recommend it. Okay, building real systems. So what do I mean by this? So, so here is a picture of a bunch of researchers who have papers and their systems. And of course, they're eager to get their papers accepted. And so naturally, they run them on some benchmarks. And these people are the program committee, right? And the program committee wants those, there's some set of benchmarks we expect you to have, right? So, we push these systems eventually, to just make it to the paper deadline, get the results we need, and then hopefully the program committee is happy. Of course, there's always, reviewer number 2. All right, so it's no guarantee that your paper is going to get in, but it really, what I'm trying to urge you to do is to stop playing with toys. All right, if you want your research adopted, the research can't just kind of barely stumble across the finish line, and the first person who picks it up and tries to use it discovers it doesn't work. And our field, unfortunately, and I'm as guilty of this as anyone out there, spends a lot of time focusing on these toys, and I just want to draw your attention to one, which is really great. So this is the Spec benchmark suite. So this is like the gold standard for CPU performance for like native code and for architecture and all these things. So the Perl benchmark is it's an old version of Perl, like it's Perl, but also an outdated version that's been cut down, whatever that means. All right, great. So there's GCC, the 2010 version, compiling itself, as I do every day. It's a totally normal workload. Like I wake up in the morning, I'm like, let's heat up my room, right? Let's compile GCC, all right? So there is one thing though, like my favorite is that there's a benchmark for Perl, which is Spam Assassin. And you may be thinking to yourself, but Emery, that's a real application. There are people who use Spam Assassin, and this is true. And I was like, oh my God, they use Spam Assassin. Kudos. But it turns out it was patched to avoid doing I/O. So it's a spam filter that reads no mail and produces no classifications. So super realistic. All right, so my point here is that users don't run these benchmarks. Yeah, I'm going to pause for a moment and let you soak this in. So users live in the real world. They don't use these benchmarks, which are really toys. And the great news is, a long time ago, these applications were all closed source. You had no access to them. But there's tons of applications out there that are open source now. You can just go to GitHub, download the source code, right? Download the workloads, right? And so if your stuff works on these things, obviously it's going to make your paper stronger, but it's also much more likely that your research will get adopted because it really works. Now, I understand there's engineering challenges to doing this, for sure. But the thing is that what doesn't kill your research makes it stronger. If you go and you take your research and you try to apply it to these real-world problems, you often discover, oh, this doesn't scale, or oh, this doesn't work in this context, or oh, I have to rethink this algorithm. And this just makes your research better. So it's a true reality check that is really, it's good for your research and it's good for adoption. All right, get your research out there in the real world. So what does this mean? It means posting your code on GitHub, right, and all your data and all this stuff, but that's not all, right? So when you create your project, the most important thing is public, all right? Make it public right away. I know it's scary, right? But it's really important to get this stuff out there. Like if you wait until you've published your paper, you've missed the opportunity to engage with users before your paper is submitted, right? Or before the next, after your paper is rejected and submitted again and so on and so forth, right? You'll get users. The users will give you results. It's good for the work. It's good for adoption. It's also great for students. Your students will know that the work is visible, right? Whatever they're doing, it's going to encourage good coding practices. It also avoids the problem of having research code that is, good programming practices. I agree. It's terrible. The worst. Anyway, it avoids the problem of having research code that's in such a bad state that you never want to release it. And I've had to deal with this situation with, it's like, hey, can I use your code? And they're like, no one can see it. I'm ashamed, right? Don't do that. Just start from the beginning in a public repo. This will never happen. It also makes it way, way easier to get these yummy artifact evaluation badges, right? You've got the thing out there, the tires have been kicked, it seems to work. It'll be a lot easier to do this. Basically in our lab, all the students go, they know that this is what's coming, they know that they're going to be producing these things, and it turns out that it really makes things super popular to have like, hey, here's a system, it works, people will download it, they'll try it. It's just a virtuous cycle. The students who are interested in having impact will come to your lab, and they will then have impact. All right, give great talks. So this sounds like super unactionable advice, right? Like, do great work, everybody. Write classic papers. The actual advice given to me once. Hey, you should write a classic paper. I was like, yes, sir. Previously, I was planning on writing forgettable papers, but now, classics. All right. So, obviously, effective communication is important for your research, but it's also really important for adoption. Like, most people are not just going to pick up your paper, right? They'll probably want to watch a video. Now, your talks are better than you think, and this is really targeted at academics right now. So if you're an academic, you have had so much practice giving talks. You are already an accomplished public speaker, right? So if you think about it, you do the math. If you are in academia, you're teaching at least 3 hours a week, all right? That's 33 weeks per year for 2 semesters. That's like 100 talks a year. If you go to one of these industry conferences, most people in industry, this is like their first public talk, right? And you've given 100x more talks than they have. So, I mean, okay, maybe I'm saying, oh, it's a low bar, so it's easy to shine. But great, it's easy to shine, right? So this is a huge win. So there's lots of stuff on the inner tubes about giving great talks. There's even information on giving bad talks if you choose to go that route. But I'm going to talk just about a few things that I don't see people necessarily emphasizing that I think are really important. So the first is your talk should tell a story. What do I mean? I think that talk should have a narrative flow. There should be a beginning, a middle, and an end. Don't just be like technical details, stuff happened, and look, results, conclusion, right? Like have a story. So what happens in a story? Stories typically have a main character. So the main character in a story is the hero of the story, or an anti-hero, but hopefully your research is heroic, all right? And the audience follows the hero on this journey, right? So who is the main character going to be? It could be a user of your software, right? It could be you. It could be an anthropomorphized version of your research contribution, but something. And we are kind of evolved to really be attracted to stories and remember stories, and this will just make your talk way easier to follow and more memorable. So, of course, show, don't tell. Use lots of visuals. Don't be scared. It's okay. It's, of course, really important to use text sparingly. I've never once heard anybody look at a presentation and say, oh, God, if there were only more words on these slides, right? I once had a student who will go unnamed. He begged me to let him put more text on the slide because I was like, reduce the text, reduce the text. And so finally I was like, okay, I give in. You can put as much text as you want as long as it's 96 point. And he said, but then I can't fit in that much text. It's like, exactly. All right, and of course, crucially, for God's sake, no bullets. All right, please, please, please don't just take the default PowerPoint presentation and turn that into a talk, or use slide tech. Please don't do that. A talk is not a paper, okay? There's like a couple people frantically like deleting things. All right. So once you've got stuff out there, you need to engage with the community. You can't just be like, hey, I met some users, and I throw it over the fence, and then I'm done. My work is done, right? Like, there's your users, and you have to engage with them. And the great thing is that this has become really easy. There's all these tools, right? So GitHub now has these issues, right? So people can put in issues. There's discussions, so there's like wikis. Slack allows you to have guests, like you can create a Slack account that's for your project. And your users can be like, hey, what's going on with this or whatever. And it's a lot less friction than email or GitHub issues or anything, right? They just open up Slack. This obviously could be bad, but in general, my experience is that it's really good. There's also Discord if you're, one of the cool kids. Okay, so names. You need to come up with good names. I think they're really important. And the reason I think they're important is because they help people hold on to ideas and talk about things in like, like a little word instead of like, here's a concept, like there's some word. So that's great. So not acronyms. Definitely not acronyms, okay? Acronyms are bad. Sometimes they're even worse than this. All right, so what should your name do? So your name should evoke the problem or the solution. It should not just be a random name, right? It should be memorable. So, don't name your system Lurleen Lumpkin. A lot of people put up these very kind of quotidian names that are very hard to remember, and that's not really great. So it's crucial that it be Googleable. Dictionary words are usually not ideal, right? If you do a Google search for your name, right? Like don't. That's actually like anyway. I'm not going to go to that story. But yeah, make sure to do a Google search for the name. I've seen names where it's like, oh Lord, you do not want to know what that means in Spanish. So it's always a good idea. Just enter the name in first. All right. So I'm just going to put up a couple names that I think are some of my favorites. So we had a couple systems for finding spreadsheet errors. One of them is called Checkcell, and the other is called Excellent. Get it? Okay. So, but all right, it's a little corny, but I think that it works. We built a system that was presented at UPSLA called Mossad, and it defeats software plagiarism detectors like Moss. You'll never forget that name. All right? So, and then we had a system called Die Hard resists memory errors, right? Your program keeps fighting. And you know it's good when you get a cease and desist letter. So everyone should aspire to receive one of these letters. They're really great. The well-known trademark, Die Hard, from Sears, because everybody would confuse my software with a battery. Like, I went to go buy a car battery, and all I got was this software. I'm so confused. All right. So finally, scratch and itch. And what do I mean by this? Like, not this kind of itch, right? I mean, real problems that you have, that you encounter in your research, are likely to be problems for others. So when you're, working on research and you run into some challenges, right, or things that just come up, like, oh, my C and C++ program keeps crashing, right? This led to the creation of the system that we call Die Hard. And Die Hard eventually influenced Windows 7 and 8. So, it was a piece of work that had, like, it turns out I wasn't the only one who had a crashing C or C++ program. There are other people in the world whose programs crashed, right? We discovered that malloc doesn't scale. And I was like, malloc doesn't scale. This seems bad. And it turns out this was a big problem for a lot of people writing multi-threaded code. So we built this system, which I'm going to talk about later. I had a spreadsheet, a grades spreadsheet with a bug, with a terrible bug, and I had to I know, it was terrible. And I had to redo a bunch of grades, and that was awful. And I was like, oh, this is a real problem. I wonder if other people have this problem. And it turns out other people have this problem. And so we're currently working on productizing this at Microsoft. All right, so that's enough for the embiggens. What I'm going to talk about next are some case studies. So I'm going to talk about some adoption successes and some adoption fails. And I think that I'm going to talk a little bit about the trajectory of these projects, a little story, if you will, and then try to get some lessons out, like what we learned from these projects. So the first one I'm going to talk about is a system called Automan. Automan is also one of my favorite names. It's about automating humans. What do I mean by this? So all of you, hopefully most of you are familiar with Amazon's Mechanical Turk. I see some nods. So Mechanical Turk is named after this, I have to share some history, this historical chess playing device from I think the Victorian era. So it was this giant device, and it would play chess, and it was defeating chess champions all around the world. And it turned out there was just a little dude inside who was a chess master. And I think the interesting part about it is he was like pretty good at chess, but he would play people who were much stronger, but I think they were so freaked out by the robot apparently moving things that they didn't play very well. So he defeated them left and right. So like the original Mechanical Turk, Amazon's Mechanical Turk is actually powered by people. So you post jobs and human beings do them. And so the dream is you could have some function that's really hard to implement, like, is this a giraffe, right? And you hand it over to some people via some API, and it comes back and says, yeah, it's a giraffe. right? So this would be great, right? It makes coding really easy. Now, you do have to pay people, and you have to figure out how much time to allot for tasks and all of this sort of stuff, but it's still fine, right? It seems great. But there's this risk that they say no, right? That they give you the wrong answer. So why could this happen? So it could be that they're just dumb. They're like, duh, that's not a giraffe, right? That could be a problem. There could be bots. So this is a real problem on Amazon's Mechanical Turk because it's like computers and the internet plus money equals corruption. Well-known law, right? It could also be that they're just evil, right? Like it's like, oh, is it a giraffe? Oh, you want to know if it's a giraffe? Oh, I know it's a giraffe. No, right? Because they're just evil. But it turns out this makes no sense in this ecosystem. So we explain in the paper why this doesn't make sense. So you can kind of ignore the existence of evil people because they can't really stay in the ecosystem. So we built the system called Automan. It's a domain-specific language. All you specify is a confidence level for every function. Like, I want to know that this is correct with 95% confidence. And it goes and it drives this statistical hypothesis testing approach that figures out what the right answer is based on some assumptions, and it dynamically figures out time and money and all this stuff. Okay, great. Total adoption fail. All right, it is not adopted at all. To my knowledge, 2 people are using it, maybe 1. All right, so it's not really being used. So what happened? So I did not embed myself at Amazon, but I did actually go to Amazon and talk to the Amazon people. Yeah, they were just not interested. And so I was like, okay. So then we presented a paper on the topic, and it got presented at Splash. And it got picked up as a CACM research highlight, so we're very proud and happy about this. But it turns out most of the people, like how many people in this room have employed Mechanical Turk, have actually employed somebody on Mechanical Turk? All right, there's like 9 hands up, all right? This is not the place. Right? So if you go to the wrong audience, like we did not go to the mountain. We went to the base of the mountain, right? And we met with a bunch of people who were like, yay, this is very clever, right? And then didn't adopt it. So we made a big mistake, but that was not the biggest mistake we made. So apologies to anybody in the audience who was hurt by this, but we implemented it in Scala. This was a gigantic self-own because it turns out nobody in this ecosystem uses Scala. In fact, when we would tell people, oh, but you have to use Scala, it's only a few lines of, where are you going, right? It would just be like a puff of smoke. They were gone, all right? They had no interest. And obviously, in retrospect, we should have done it in Python, right? And so lesson learned, right? We made a few mistakes. These are mistakes. I mean, you can't expect maybe Amazon is going to do anything, but you do need to go and find the people who are interested and then give them a tool in a way that they can actually use it. All right. Second case study, stabilizer. So there's this great paper called Producing Wrong Data Without Doing Anything Obviously Wrong, exclamation point. I aspire one day to have an exclamation point in my papers. And it turns out that memory layout drastically affects performance. So what do I mean by this? I mean crazy things like an environment variable being 1 character bigger or smaller can make a program run 40% faster or slower, because of cache effects, all right, that I'm not going to go into. So we were like, well, this is clearly a problem, right? People want to know if their performance changes are making a difference, right? So we built a system called Stabilizer, and Stabilizer works at a very high level by repeatedly randomizing the layout of everything in your program. And so it can't be biased if everything is random, all right? It's like random RCTs. So this means that if you get these results out, you can take them to the bank. The effects are not due to memory layout. And so what we showed is that it also enables a kind of statistical hypothesis testing, and we jokingly refer to the way that most people look at this as eyeball statistics. We're like, yeah, this looks better, but that's not statistics, right? So you want to be able to actually have some statistically sound thing, and so the effects are not due to memory layout. And we found, when we ran some experiments, that -02 versus -03 in LVM at the time was indistinguishable from noise, which is a surprising result, right? I thought. Okay, total adoption fail. So it turns out that we had a solution to a problem that people did not want solved. All right, what is that problem? Well, sometimes people's results looked like this, right? Like very, very narrow performance improvements, and Stabilizer would be like, yep, not significant. Oops, turns out that there's not many people who are like, hey, I would like a tool that makes it really unlikely that my paper is going to get in. All right? Like, hey, I did a lot of work and it's insignificant. Please accept my paper. All right? So there was a recent blog post that was really insightful. And it analyzed why stabilizer hasn't been adopted. This guy was like, stabilizer's awesome. And I was like, yeah, you're the bomb. And he's like, hey, why didn't it get adopted? And I was like, oh, you're right. From a results point of view, developing a stabilizer tool seems likely to come up with a bunch of negative results, demonstrating that people's performance improvements were actually not statistically significant. And somehow this did not occur to us, right? That people would be unlikely to adopt this. So clearly an adoption fail. However, at the end of the blog post, this guy showed something that I didn't even know, that there's a project for doing WebAssembly JIT benchmarking that is apparently going to adopt some of the approaches we had, basically for checking for performance regressions. And so it's like, is an adoption fail? It's still mostly a fail. All right, so now I'm going to talk about a success. So this was my PhD work. So this is the Horde memory allocator. The name is actually a play on how the allocator works. And it all started because I started my PhD working with my first advisor on a C++ library for parallelism. And it was very cool in theory. In theory, it was provably scalable. You would write your program using this library, and it was guaranteed to scale, except when it didn't. All right? And so I wrote some apps. And it not only didn't scale, like if you put it on 2 processors, it ran at like a fraction of what it ran for 1 processor, right? It's like, oh Lord, it slowed things down tremendously. So as a junior PhD student, I was like, oh Lord, what is happening, right? Like this is provably scalable, and yet it is not scaling. I'll go back to the professor and say, hey, your proof might be wrong, right? And so I was convinced I was doing something wrong in my code. And I couldn't find anything. And so then I looked in the library, and I couldn't find anything. And then eventually I found something. And I found this not-so-smart malloc. So it turns out that the allocator that Hood was using was really bad. And I was like, OK, I'll just replace this with some off-the-shelf, actually good allocator and move on and continue to do parallelism work, right? So let me give you a glimpse of the problem here. I went and looked for a good allocator, and it turned out there was not one. All right? So they all suffered from these problems. So the default allocator on the system I was using had 1 big lock, not exactly scalable. So there were these nominally scalable allocators, but they had other problems. So this is, of course, a problem of false sharing. And so what would happen is the allocators would actually carve out pieces of the same cache line and hand them to different threads. And so those threads would just be working on nominally independent things, but actually they were sharing the cache line, and this would drastically degrade performance. All right. It also gave rise to this phenomenon that we call blow up. So these past multi-threaded allocators would basically leak memory, which is like the thing that memory allocators are definitely not supposed to do. Otherwise, why would you have a memory allocator, right? It's supposed to manage your memory, not leak it. And so what would happen is you could have one thread allocating, and then it would give the memory to another thread that would free it, and that memory would just accumulate on their own local heap, and until literally the system would run out of memory. So we had a program where you'd link it with one of these things, and it would run for 5 seconds and then crash, just because you're using a scalable allocator. All right, so I'm going to show you Horde on one slide. We called it Horde because it always grabs big chunks of memory that we call superblocks. It makes these superblocks, it keeps them in pools that are exclusive to each CPU. Turns out that this avoids locking and false sharing. As you've allocated these things, eventually you free them, and to prevent this situation of blow up, basically the empty space allows, like once it crosses some threshold, the memory is moved to a global heap where it's available for everybody else, and we could show that this provably avoided locking and blow up, and this took us from here to here. Okay, yay, victory. All right, so it was like, I have a better mousetrap, everybody, and so I went to the leading social network of the time, and I posted a USIDNet tweet, and I made the code publicly available, and I announced it, and we got users. So we got users, and so this is actually the abstract of the paper. So this is, it helped find issues, refine the implementation, and it got these great real-world results that we were able to cite in the paper, which is awesome. So we had users, and we got these results, and I'm sure that this helped get the paper in. All right, so what did I do? I did try to embed myself. So I went and got an internship at Microsoft Research. where I tried to convince them to replace their allocator with Horde. That did not quite work. Actually, it's pretty funny. It turns out I was able to finally link Horde with all of with Office, and every one of them crashed. And it turned out that the reason that they crashed was because they were all full of bugs, but the Windows allocator was really generous. So you'd ask for 17 bytes and it would give you 32. And you could go crazy at the end, but if you used Horde, Horde was you asked for 17, you'll get 24. And then you'd write your data out of bounds and it would crash. And so that led to some interesting work later, but the best thing that led to was that I got adopted by my now longtime colleague, Ben Zorn. So adoption success right there. And then at another indication of adoption, I got another call from lawyers, this time for patent infringement. This was quite a saga. Find me later, I'll tell you more about it and how we beat it. But anyway, speaking of infringement, I hope Matt Groening never sees this talk. But anyway, it got adopted, it got picked up by a number of companies. But at the end of the day, I'm a parent. We all want to just actually impress our children in some way, right? Oh, I'm this geeky person, whatever. I'm like, hey, I did the software. It got adopted by all these companies. And my daughter was like, meh, right? Some companies I've never heard of. Why do I care? But then it got adopted by Apple. So in Apple's memory manager, there is an actual citation in the comments, which is the best citation ever. All right? And I showed this to my kids. And so I got, okay, that's actually pretty cool. So adoption success. I have to say, by the way, that this whole citation of your papers in code is so awesome. This actually happened with Android Studio. We found out about it by total accident. They adopted one of our pieces of work called Bleak. And it's, anyway, like I said, best citations ever. All right, so to conclude, this talk has been aimed to help you embed in your research, right? You get out there and embed yourself, go to the mountain, build real systems, get your research out there, give great talks, engage with the community, name those names, and scratch an itch. So I encourage all of you to go out and embed in your research. And I want to conclude by thanking some of my longtime collaborators. First, Catherine McKinley, who adopted me as her advisee. Ben Zorn, who adopted me as his mentee. And my students, Dan Barroway, Brianna DeVore McDonald, Charlie Kurtzinger, and John Vilk, who all did some of the work that is in this talk. Thanks for your attention.
Great talk. So one thing you didn't mention, looks like a lot of systems get adapted by kind of sacrificing the graduate student with the project to a company. Things like LLVM, Halide, all those things basically shift the student. Right now, Legion, so all these things. So you didn't have that as a adaptation technique.
Yeah. So I mean, if you're able to sacrifice your graduate student, I should repeat the question. So the question was basically, I didn't mention sending your grad student off to a company to go implement these things, and you're absolutely right. I didn't mention a lot of things, right? But LVM is an insane success story. And Halide is amazing, right? And I think that if you can come up with a way, I think this is hard, right? I don't think it's easy to say, hey, Apple, here's this compiler guy who came up with a new compiler infrastructure. How about you hire him to keep working on that, right? That's amazing that worked out. So I don't understand or know the alchemy, and it would be great if you have some thoughts on how to make that replicable.
Hello? Okay. Thanks for a really, really cool talk. So I wanted to see what your thoughts are about research adoption within the academic community, whether it matters, how it relates to the kind of adoption you talked about, and how one can make that happen.
Yeah, that's a great question. So I've focused on companies and the real world, quote unquote, as opposed to academia. But if you can get your infrastructure adopted within the academic community, that's still adoption, right? It's still a kind of impact. We tried to do this. So we had a framework that we developed for building memory allocators, and that has not really been picked up. But Steve Blackburn and Catherine and an army of other people put together this MMTK, memory management toolkit, that got adopted by a bunch of researchers. And it's a ton of work. I mean, I think there was a lot of evangelism and a lot of, a lot of engineering and a lot of effort pushing those things. But the good part is that it was, in a way, like whatever they did to make MMTK better also helped themselves, right? So there is a virtuous cycle there at play. So I think that if you're in a situation like I worked on my infrastructure and tried to get it out there and people weren't that interested in using it, there was some other kind of infrastructure that came along that's clunky and whatever, but people were using that, fine. But I kept refining it and it was good for us and for my students. So we've used it. So I think that if you are already working on building some infrastructure and you find it to be reusable or of value to yourself, then you can keep building it, and even if it doesn't get adopted, it's still a win.
Hi. Great. Obviously, a lot of work to create tools that are robust. And so I was wondering if you thought it was equally worth it at every stage of your career, from solo PhD student to senior faculty with an army beneath you, or if maybe it was more appropriate at some stages than others.
Yeah, great question. So I mean, I don't know how much is being picked up, but the question is basically like, it's a lot of work to do this. There are trade-offs. When do you do it? Different stages of your career. Have you always done it, and so on. So I've always done it. So I don't know anything different. I just am personally gratified by these things, and having users is, having a paper accepted is great, right? We all love that. Who among us does not? Right? It's like, oh darn, another paper accepted, right? It's great, but I value having users more, but I think that it's also important to understand, like, some of my most adopted pieces of work are also my most cited, right? So I don't really think the two are in opposition, right? So it's like, well, if you build a system and people use it, guess what? They're gonna cite you. So I think that it's, there's no reason to say that the two have to be divorced. With respect to graduate students, I've never had an army of graduate students. The most I've ever had at one time is, I think, 6. And my steady state is more like 4 to 5. So it's a pretty small army. Just they're devoted and great. And I think that, I think that it's honestly motivating for a lot of students, right? Like, the students also derive a lot of pleasure from, like, oh, people are actually using this and you can go talk about it. And it's great for getting a job, right? Like, you go on the job market, the talks where it's like, this is being used by Amazon, right? That attracts a lot of attention. Hope that answers your question.
Hello. Hi, Emery. Right back here. Awesome talk. So actually, I just wanted to report a bug. I thought it'd be great to
file an issue.
But more seriously, I mean, having been on both sides of this, right? Having been in industry, now in academia, the thing with getting these tools adopted in the real world is that, users want confidence that this is going to be maintained, that their bugs are going to get fixed. They don't want to depend on an academic tool, integrate it into their system, and then later on, everything breaks and they can't get any support. So I think it's obvious that you've overcome this obstacle, and I wanted to hear more about how you did this, particularly given conflicting incentives to publish more papers and graduate your students and all this kind of thing.
Yeah, good question. So, I mean, I agree that people don't necessarily want to take a dependence on something that runs the risk of somehow being abandonware. If you're lucky enough to build enough of a community around it, then this kind of doesn't happen. People are still banging on things and reporting things. The graduate students I've had have generally been interested in continuing to maintain their work. Like, their name is on it, right? So there's kind of an incentive to do this. It's not, maybe it's not their first priority, especially if they're in industry, but I think that the ownership, like, it's really important, right, that the students own the work from the research perspective as well as the software perspective. So I think that we don't have any projects that have been adopted and then withered away because the students have just stopped answering issues.
Right, great talk. I'm on the other side of this adoption thing.
You're opposed to adoption?
No, I'm actually doing adopting. So like, Roblox, like, we pick up, like, systems that are out there in the academic literature, but pretty much consistently we re-implement them. So what we're interested in is reusing algorithms. We're not that interested in reusing code. So, which means that I'm going to give you a bit of a pushback about one of your letters. So B, so the build real systems thing. That, I mean, different companies are different, but for us, that's actually not the thing we're interested in. What we're interested in is the reusable brain stuff. So I was wondering what your thoughts would be on that.
Yeah, so I mean, do you always need to build real systems? I don't think you always need to do every one of these things. I think they help. You know, if somebody, you know, there's obviously areas that are just purely algorithmic, right? Like if somebody is a theory person, they publish an algorithm, it's nice to have an implementation to validate they haven't missed anything, like that there's some big giant constant factor or something, right? And so that's certainly positive. With respect to the kind of stuff you all are doing, if you're adopting like type theory and things like this, I can see how, you know, the code would actually potentially be a burden. But on the other hand, maybe it was valuable that it was implemented once and people tried it out and experimented with the type system to give confidence that it was something that you were then going to adopt. I think it's unlikely, and it's a possible path, but it's unlikely somebody just publishes an algorithm and then it's so obviously a good idea that you go and implement it. This does happen, right? But maybe not always.
Thanks very much for the great talk. So first, how many times do you have to watch The Simpsons to make such a great presentation? And second, can you share some secrets of how to make this almost a text-free and meme-dominated presentation?
So Google image search is your friend, and a healthy disrespect for copyright law. Fair use, everybody, fair use. So yeah, I mean, I think that, you know, at some point I just decided, look, people prefer visuals. I prefer visuals. Let's try to make things visual. And I just look for images that reinforce the point or can stand behind a point I want to make. And sometimes you have to make them yourselves. But there's a lot of images out there. And with DALL-E, soon you'll just be able to say, write a visual fantastic talk for me, and it'll produce images, right? I actually, to be honest, I would love to, so I don't have a DALL-E account. I would love to try making some of these things. I think actually it could be really an effective tool.
Can you hear me?
Yeah.
Okay, there we go. Really great talk. Thank you for that. I want to come back to Stabilizer. You nerd sniped me a little bit. And also what you said about going to the mountain and users. So I worked on V8 for a long time. And what we noticed is that software performance regresses little by little over time. Very small changes, very small reduction in performance, 0.1%. And so adding noise to that makes it harder to detect those things. And I think that there's a use case that's really important for being able to do performance regression over time. And adding noise to that may be difficult to notice those things. Do you have thoughts on that?
Yeah, that's a good question. I mean, I think, so, I mean, you know, certainly the challenge that Stabilizer addresses with performance regressions is that you made a change. So there's two possibilities, right? So on the one hand, you optimized your code, and it got faster, but it turned out that you didn't optimize your code. You just allocated an object, and things got laid out in a nice way by happenstance, and then that could be brittle. The other thing, of course, is that you degrade performance, and that degradation, you might be tempted to roll back, but it again could be an accident. Now, if it's really, really small, it is the case that Stabilizer, it'll just require more runs to weed out what's happening, right? So the noise that's there is not just noise in a kind of like, there's random noise, and the sort of like, oh, it's totally random. No, it really is random. And because it's random, it means you can factor it out. So you may have to run a bunch of runs, but you would get eventually the signal, I believe.
Hi. One concern I have about like embedding with companies and pushing for adoption of my work is that it will become like patented or owned in some way that I can't build on it anymore. So like, what is the reality of that concern, and how do you approach that?
Yeah, good question. IP. So, so let's see. So first, if you have released some open source code while you're in academia, no company wants to adopt that stuff and say, oh, we're going to put a patent, do a patent around it, or do this, because it's contaminated, right? So if you've done something before you show up, this is insurance against that ever happening. Now, if you do something while you're on the company dime, it does belong to them, right? Do they want to make a patent? Do they want to file a patent for it? You know, in a lot of cases, there's a lot of companies like Facebook, for example. Facebook is like, you can have everything. I'm speaking as a Facebook lawyer, right? Like we don't care because Facebook doesn't care, right? They have the social network and all the evil and stuff. And so, the code is not the problem. Really? Nobody's on the same page about the evil? Okay. But yeah, I mean, your mileage may vary. It depends on the place. It also depends on your institution. So UMass is really generous about IP. They're like, you created the IP, please commercialize it if you think it's going to make us a bunch of money. But they make most of their money from pharma. So they're like software, schmoftware. They kind of don't care. So if you can just convince your institution of that, that's the way to go. But yeah, in general, I mean, you have to be a little careful about IP. But I have not seen this as a big problem.
Hello, there we go. So I'm from the industry side of the world. So I work on Apple, on the Swift programming language. And so we're looking for the great ideas to adopt. And so I wanted to emphasize your point about putting your work up on GitHub, put a README file that makes it easy to use, because when we see a paper, we want to be able to try out the ideas real quick. Just get a prototype going, see if we can replicate the results and if they work in our environment. Because if we get that far, then we'll probably go and rewrite it anyway, right? To do it our own way, we'll have our own code, it'll integrate really well. But that initial artifact up on GitHub gives us the confidence to go forward with an idea. And the other point I wanted to bring up is that for programming languages, most of the interesting programming languages out there, they're open source. So you can embed yourself from your own desk, in your office at home by working with an open source project that you care about and sort of semi-productizing your idea there. You don't have to go to Microsoft Research. You don't have to go into industry to do that. Right.
Yeah, these are great points. Listen to this man. The ability to try out your ideas, right? Like, oh, you download it and you run it. This is really, really important for industry, right? So it's like, hey, here's a paper. Paper seems interesting, and you try it out. Oh, hey, it really works, right? This is huge. The other part about open source communities. So I've been doing some work with Python lately in my lab, and so I will say, I mean, I've kind of gone to the mountain. Like I've gone to PyCon, and there's a Boston area Python group and all this stuff. But the communities can be really open and welcoming, and they're interested. And there's a whole process for bringing people in and doing open source and having contributions. You can really make a difference that way. So excellent points.
There we go. Perfect. So you talked a bit about how the industry adoption that you've aimed for has helped your papers get accepted or cited more often, which is useful because those are some of the direct measures by which academic success is measured. But that means that the industry adoption in some ways is an indirect comment about how industry adoption is directly valued by things like tenure committees or grant review committees, that kind of thing.
Yes. So the question that got a little broken up was basically, hey, you're getting papers accepted in citations, and that's how we normally judge success. But what about industry adoption? It turns out letter writers are aware of these things, and they matter. And it matters it matters for awards. It matters for promotion cases and for tenure, for full. This stuff all gets mentioned. Of course, I haven't seen my case, right? But I know I've seen lots of cases. And when people have had this kind of impact, it's always like, look, this shows the value of the work. So it's absolutely the case that it is there. It's just not a numerical measure. There's no H index for your systems, right? There's no S index, which is maybe a good thing. Right. Okay, great. So Margot said pick a license. You should license your software. And so when you go on GitHub, it makes it very easy to pick a license. Your university probably has some pre-approved set of licenses that are very generous. So I recommend the MIT license or the Apache license. These are very company friendly. I do not recommend GPL of any stripe. If you GPL something, companies run away screaming. They're like, contamination. And so if you use one of these more generous licenses, it just makes everything much easier. And honestly, if you go the GPL route, you just delete it from GitHub. People don't want it. All right. Sorry. Yes. Yeah. So I know somebody from FSF is upset now, but I'm still right.
So at PLMW yesterday, John Rigger asked a really, I think, probing and provocative question about what we should work on hot topics or maybe deliberately work on not hot topics, because we're a broad community, we do lots of different things. And I wonder if you had thoughts about the same thing with respect to targeting adoption. So a lot of people like you work on things that I think amazingly have a very short turnaround time for when they could get adopted by industry. What about people that want to work on things with longer time horizons?
Yeah, so I mean, I think that you know, the sort of like short-term versus long-term thing, I've always been kind of skeptical of. I think it's very easy to say, well, this is going to have impact. You know, give me tenure and promote me, and then, you know, after I'm dead, you'll see, right? It's like, okay. But I mean, clearly people should be thinking about these things, but I also want to say, you know, a lot of these things that get adopted, it's not like, oh, you just like, there was like a hole and you filled the hole. Typically, it's like, well, you discover a whole new thing and that happens to solve a problem and has practical impact. So, I mean, I don't think of these things. So I will say that I do advocate problem-oriented research. That's my research style. I don't think that's the only style, but you know, if you do want your research to be adopted, if that's something you care about, then not adopting problem-oriented research means you'll be producing a lot of stuff that may eventually find application. Whereas if you have a concrete problem and you're like, look, I really think this affects a lot of people, then it's way more likely it'll get adopted. But this is really a personal choice. I don't think that, you know, there's a one answer, but it depends on your values and what, you know, honestly, every day you're going to be working for years, right? You're going to be working every day, and you know, as a faculty member, literally every day, but lots of days, right? And you want to be happy and excited when you go to work, even if, you know, you're just walking down the hall to your, you know, computer. But you know, you show up, you want to be like every day should be like, yes, I'm going to do this. So whatever it is that drives you, that's what you should follow. And for me, it was building real systems, getting stuff out there, solving real problems.
So you talk about this work on stabilizer, which reveals some drawbacks of the evaluation, actually receives some pushback from the community. So I wonder how often do you experience, how often this is the case that there were some, this kind of confrontational or some research that actually reveals the drawback of community get pushed back because of basically moved other people's cheese, and how we should navigate with these kind of projects.
Sure. So, I mean, briefly, I mean, I think that Stabilizer was an interesting case. I mean, an Automan had a different kind of situation with the community. I mean, it's not like it was pushback from the community. The papers got accepted. They're well cited. They're, you know, some of them won awards. It was just that we thought something would get adopted that we didn't think it through. It's like, of course, nobody wants this. At least the use case we thought of. And now people are repurposing it, and that'll be great, hopefully. But yeah, you know, look, sometimes things don't work out. That's okay. There's more things to do. And it did work out in a way, right? It worked out in the traditional measures. We had a good idea. It was really interesting, intellectually rich. We produced something, papers out there, and it didn't get adopted as a system yet. Fine. It's okay.
Okay, how do you deal with double-blind reviews and very popular open source software that goes with that project?
Yeah, that's a good question. So as you probably are aware, I'm a fierce advocate for double-blind reviewing. One of the things that that people do to address this problem is to use code names. So you submit a paper on, you know, system X, right? Instead of whatever the system is. Maybe come up with a better name than system X. But I've seen papers like this at systems conferences as well as PL conferences. And, you know, if you know what the system is, maybe you'll know, but maybe you won't, right? And, you know, obviously if a lot of time has elapsed, maybe this is a problem for double blind. I don't think it's generally a problem for the kind of work we do. But, you know, the paper that was on, like the Spark paper, came out at a time when it was riding this adoption wave, and I think there were still a lot of reviewers who were unaware of Spark, right? So they, you know, you called it spook or something, and nobody would have any idea, right? So I think it's easy enough to obfuscate it, but at a certain point, you're right that it could become an issue. Yeah, so this is not a problem. I've seen all kinds of phrasings like, large internet company X uses this and things like that. It's very easy to navigate a lot of these things. Look, the deal with double blind is you don't want to put it in somebody's face, right? And say, hey, I'm the person who made this and this is famous and you should accept it, right? You want to make it have, it has to be maybe not something they're going to stumble upon that's going to break double blind. It's, there's degrees is really the short answer.
All right, thank you all of you for the great questions, and let's thank Emery for the really, really interesting talk.